This webinar will go through the OrCAD PCB Designer Professional level of tools. We start off, this is kind of OrCAD PCB Designer, all of the Cadence PCB tools as they come out of the box. So there's several ways to drive the tools. We've got a menu-driven system. We've got some icons. So you can obviously choose a menu, choose a command that you wish to do, and then do something to the components. You can choose an icon, so the icons obviously match the menu flow, so it's that kind of typical option. We can assign shortcut keys or enter command line keys by typing them in. Or we can use like the hover mode, so we can hover over what we want to affect and then do a right click and then do things like move, rotate. So for a symbol, that would be different if we hovered over a track, for example. So looking at the PCB we have in front of us, we've got some stuff that's kind of been placed and routed already. We can just scroll in with the mouse wheel just to kind of see what's going on. You can see we're getting useful things like embedded net names into the tracks, into the pads, and also on the copper shapes. Allows you to quickly identify the nets that you're working on. We've got some components that have just been kind of placed at the top edge of the board, so they need to be put into the main part of the PCB. I've got a couple of components here. And I've also got some components in the placement bin. So these need to be placed onto the board. So I can select a checkbox in the placement bin, and effectively that part is then attached to my mouse, and I can come along and just place that down in the design canvas. I can also go place components manually, which allows me to then choose from this list. Similar cut from the placement bin. I can also do things like right mouse button mirror, which will flip it to the back side of the PCB. And also do things like right mouse button rotate, and I can rotate in either direction, and also at any angle. So if I wanted to do something at 11 degrees, for example, I could obviously do something at 11 degrees to get the orientation correct. Place the components down one by one. But obviously placing from a list is not really as intuitive as it could be if you're placing directly from maybe the schematic. So what we'll do is we'll leave the command active, we'll hide the placement bin window, and then what we'll do, we'll bring the schematic up. So we've got the PCB and the schematic. I can then single select a part in the schematic, and it then becomes attached to my mouse in the PCB, classed as cross place. I can do that individually on components, or I can also draw a window around a group of components that I want to bring in, and then going to come in alphabetically. So obviously the diodes, then the transistors, and then the resistors as well. Once all the components are completed, I end the command. You can see that the placement bin is now empty. So while we have capture open, I can do things like cross probe. I can select a part in the schematic, and it's going to zoom and center it on the PCB. So I can work my way through and find the components that I need. That's also going to work on net, so I can obviously select a net, and it would then highlight the net for me in the PCB editor canvas window. And you can chop and change between what you want to select. Great when you're trying to do a peer review check. This is going to work from schematic to PCB and PCB back to schematic. Okay, this next section we're going to go through something called place replicate or design reuse. And what this does is give you the ability to speed up your design and reuse something that you've already maybe done on a previous design, or maybe you've done once already and you're repeating that. In this example, I've got an LED block. It's 4 components. Maybe it takes you 5 minutes to place and route each little block. If you're doing that 4 times, that's 20 minutes. If you've already done it once, you want to try and save as much time as you can. So I'll window select all of the components, hover over any one of them, and then I can do a right click, place replicate, apply, and then choose the block. The block is in a library location. If not, I can just browse to any Windows folder if I needed to. So I'll pick LED, and then I'll effectively start to place the modules down on the canvas. Once they're done, obviously all I need to do is that single connection, but I've saved myself 20 minutes worth of time. I've got useful functions, so I can hover over one of the blocks and do a swap. So we'll swap the 2 modules. Let's do that again. So we'll swap the 2 modules. So we've now sorted out any crossovers we had from a tracking point of view. Eases the routing. I can also window select them, and we'll do a hover, and we can align the modules. So we'll align the modules in the X direction, and then we can also do that in the Y direction, specify a specific gap, and then we can obviously increase that value or decrease that value. So once complete, I'm zooming in, I'm getting a DRC error. It's a design rule check error. I've got an issue with placing of this module. So if I have a look, and I'm going package to place, keep out spacing, the routing looks okay, I've got no component issue, so potentially I've got a 3D issue. What we'll do is we'll click on the 3D button to launch the 3D viewer. So the 3D viewer uses step file technology, so the step files are actually mapped to a PCB footprint. I can obviously scroll in and out with the mouse wheel. I can use the shift and right mouse button to spin and rotate, as any other kind of standard MCAD tools use. We can start to see obviously step models. So I've got a cover, I've got some step models for some of my parts, I've got all the different layers available to me on the PCB. What we'll do is we'll just come along and we'll turn all the step models off for now. We can zoom in and let's have a look at the layers. We'll turn all the layers off and then quickly look at things like the top layer. I've got a silk screen outline so I can see the silk screens on the 3D view. We can start to maybe turn on some of the inner layers. And if we scroll in, we'll just have a look at some of the vias. We start to see the cross section, so you get a really useful view of your PCB from an internal point of view to see what's going on. We also start to see things like the dielectrics. So if we're looking at the actual thickness of the PCB, if we turn all of these on, you can see we're getting an actual individual dielectric with the copper layers, so a really accurate 3D view from a component point of view. Let's turn all our symbols on, and then what we'll do is we'll just turn off the cover, and we can start to see the step files that are used specifically for the 3D models, which can give us a good representation of what's going on. So we'll turn our cover back on, and then we can run actually a clash detect. Let's find out what that DRC was causing. So if we hit the calculate button, what happens here is that we're now doing a step model to step model comparison. Obviously the cover is a step model that's been imported, and after about 10 seconds roughly, the clash detect is complete, and you can see I've got potentially 6 issues here. In this kind of process, normally what people do is they would export an IDX or an IDF file or even a step file, go to the MCAD engineer. The MCAD engineer would then run a clash detect in his tools that he's using, SolidWorks Pro Engineer, and then send the information back to the PCB designer. He would move the components, and then you would repeat the step to make sure you had no clashes. Being able to do this inside PCB editor tools can obviously save you quite a lot of time from that point of view. You can see the clashes straight away. I start to get an indication. So when I select what the components are, I can obviously select the cover, and it would highlight. I can select the individual diodes here, or the LEDs. I get a blue diamond to show me what's going, which component is effectively clashing, or what the issue is. It changes colour. So obviously we select a different LED. You can see I get the colour change. And even if I can't see it after that, I can use the right mouse button, locate, and the component will flash 5 times to give me an indication that there's an issue with this part. And you can see that the cutout inside the cover hasn't been created properly, so I need to go back to the mechanical engineer and say, you need to give me a new cover. We'll close the 3D view down. Another quite useful feature, I can obviously select an individual part just by using the tab key to cycle through the symbols. We'll do a right click and we'll do a 3D view. So if I wanted to do a symbol inspect, looking specifically at the connector, I can make sure that my connector is mapped properly. You can see the pads or the holes for this connector, and I get a very good realistic view of the actual USB connector. So what we're going to do now is take the place replicate up to the next level. I've got a couple of FPGAs, some memory, some decouplings, some connectors, some switches. If I placed and routed all this in one go with some length matching and stuff, it might take you a couple of days to kind of do all this. And if I've done this on a previous design, saving 2 days of work in a PCB design is very huge, really. It's going to save you a lot of time. So we'll do a right mouse button, place replicate, apply. This time I'm going to pick the processor block. Now you can see it's not using the reference designator. All the reference designators are different. It uses a PCB footprint, a point-to-point connectivity, and actually the device type, which is going to give you the value information. So you can see I've got an unmatched component, RM1. If I select that part, you can see that the seed value was 47 ohms. If you actually find out in this new design, it's now 100 ohms. So it's a mismatch, but I can say let's go and match RM1 to RM1, and it's now using that new resistor value. Click OK. And then once it's processed, the module is then ready attached to my mouse for me to go and place with inside the PCB. So we'll just scroll down. I can pick a good known location. So obviously I've got a really useful function. I can hover over an object, like an origin point, a tooling corner, and do a right click snap pick to, which allows me to choose something like a pin in this example, but I can also choose an intersection. Maybe my mechanical engineer's given me a DXF file, and I've got 2 lines crossing over to give me an intersection point for pin 1 of a connector. Makes it a lot easier to place components, and it's available in most commands. We'll just disband the group, and then if we go into etch edit mode, we'll just draw a window around a group of components, and then we can do a right click 3D view to again have a localized area view of what's going on. So you can see I can see my 2 memory devices here. In this example, what we'll do is we'll just turn the symbols off, so I can start to see the pads, the tracks, the vias quite a useful view when you're trying to look and see what's going on with your routing. So I've placed this processor block and I'm getting a couple of DRC errors. So let's simplify the display. If we go to the visibility tab, we can enable the layer select mode and then just turn on inner layer 1 and some DRC errors. And if I hover over the actual DRC error, I'm getting a relative propagation delay error. We need to find out what's going on here. So what I'll do is we'll launch Constraint Manager. So we can launch Constraint Manager from the icon. We can use the setup constraints to run Constraint Manager. This is where the Cadence PCB tools set all your rule sets. So we have a physical tab which allows us to effectively create a set of rule sets for, you know, I've got a default rule set, differential pairs, HDI, power, and I can have different track thicknesses, different vias that are used, and then those rule sets then get applied to effectively the nets, the differential pairs, any buses, and I can just pick a rule name and then apply that to that specific net if that's what I wanted to do. I also get the ability to set rules by region, or constraint regions they're called, which allows me to have rules by area, so I can have different track thicknesses inside a BGA, for example, or in a flexi area. I also have a spacing set of rules, so I can set up all my line to line, my pad to pad gaps. And again, you set your rules, you apply the rules to the nets or the objects that you've got, or also into the regions of specific spacing areas. I can also define things like class-to-class rules, which allows me to set up, if I've got some maybe primary and secondary on a power supply, for example, I can set up a specific set of rules between those two different groups of nets. And then I also have some interlayer spacing, which allows me to set up some dielectric DRCs when I'm doing things like Flexi-rigid. So if I wanted to do some transition zones to via breakouts or solder masks, I can start to check some DRCs for that. From an electrical point of view, which is where we're looking at, obviously I've got wiring in the professional base level, so I can specifically route a net or control how a net is routed, and DRC to that, which I'm going to show you in a minute. We can set up an impedance value, so actually put a specific target impedance and route to that. Propagation delays and total etch lengths from a length matching point of view. Differential pairs, if I'm not using it from a physical point of view, I can actually set these up electrically and include things like a static phase control. And I also have a propagation delay, which is the match groups. When I want to match a set of nets, like DDR, for example, I want to match them to a certain target length or value. So what we'll do is we'll analyze this match group. You can see these are the couple of DRCs that I'm having. So I've got two DRC errors here. And the reason here is that I've actually imported the routing. In this version of this PCB, I actually want the delay to be tighter. So what I've done is I've tightened up the tolerance on this delay group, on this match group, that allows me to then show me a DRC. So if we go back to back to the main design, you can see these are the two tracks that I need to go and correct, and I just need to add some length. So what we'll do is we will do a delay tune command. I can pick the track. I'm getting a heads-up display, changing from red to green. Red when I'm not meeting the constraint, green when I am. I now know I'm meeting the constraint, the DRC disappears. We can also use a command like slide, and I can do really useful things like I've got a kind of I want to maintain the shape of this delay tuning. So if I slide this individual segment, I can actually slide it, and it will it's like a 3-segment slide. It will maintain that shape for me, which is what I want from a routing point of view. If we go back to Constraint Manager, you can see that those two DRCs have now been cleared. So using the layer select mode, we'll select the top layer and the bottom layer. Let's use the control key to turn the two layers on at one, and we'll just turn off the keep out areas. So I've got a specific net that I want to control how it's routed. I've got an FPGA going to 2 memory devices, and what I want to do is I want to come out of the FPGA, go to a via, and then match the length from the via to both of my 2 memory devices. The way I would do that is using something called Edit Net Schedule. I then pick the net, and you can see everything kind of grays out, and it highlights the legal points for this net. So I'm going to start off with my FPGA pin. I'm then going to pick the via as the second point, but instead of picking the via, what I'm going to do is I'm going to do a right mouse button, insert T, and I'm going to insert a T point or a virtual point. I go to memory device 1, back to the T point, memory device 2, and then I do a right click done to complete. I then get this kind of this virtual point that I can effectively right click and move. That's now attached to my mouse, and then I can be very specific and actually let's snap this directly to the via itself. Once that's done, I can then go ahead and route this net. So what we'll do is we'll just launch the add connect command, and we'll start to route this on the top of the board. And we'll also change the layer to the bottom of the board and then route this side of it. So just from a routing point of view, you can see obviously this half of from the T point to this memory device is longer than this half. So let's actually set some DRC rules up to be able to check for this. So if we go back to Constraint Manager, first things first, we'll go to the wiring. I scheduled this net and I want to make sure that when I route it, I don't break that schedule. So first things first, I can do a verify schedule. It does meet the schedule because that's the way I've routed it. If I hadn't routed it from the T point directly to the memory device, I would get a fail here. I can also set up a stub length. So let's go and set a stub length of, I don't know, 0.5 millimeter, which allows me to use the same fan out via when I'm routing the net. Let's go back to the propagation delay worksheet, and what we'll do is we'll pick the net and we can do a right click, create something called a pin pair. This now allows me to split that net, the whole net of DDRA7, into the individual point-to-point objects. So I've got my virtual point or my T point, and I'm going to go from the virtual point to one of the memory devices, click apply, and then I'm going to go to the other memory device and click apply. We'll then close the pin pairs. Once the two pin pairs are there, I'm going to create a match group. We'll call it address. And if we scroll up, all the match groups are at the top alphabetically. So I can then specify that I want these to meet within a millimeter. We'll then analyze the match group. And you can see I need to go and make a change here because I've got a length mismatch. So what we can do is using the delay tune command, add some extra length. I get the heads up display here going from reds to green. If I go too far, it will go red again. So I can then actually see the value that I want to get this set to. It goes green, the DRC disappears, and if we go back to Constraint Manager, my target lengths are now in, the Constraint Manager is green, and we're meeting the rules. So let's do some basic routing now. I've got some buses coming out, or a bus here coming out of this IC, and I want to be able to route these together. So we'll invoke the add connect command. We'll window select all the connections, and then they're going to come out based on the default, the last layer that I routed at, which was the bottom, and on the pin-to-pin spacing they're coming out from the via. So I'll do a right click here. We'll go to, let's change the active layer to inner layer 1. I can also do a right click route spacing and pick maybe the minimum DRC. That allows me to route the tracks where I want. I can come out, I want to add a via, so we'll just do a double click, pick the layer we wish to go to. In this example, I want to go to the top. I can change the via pattern, so let's make that a staggered via pattern. We'll drop the vias, and obviously I want to now finish this routing. So let's do a right click and we'll go to single trace mode, and then we can literally just come along and finish our routing very, very quickly without too much issue. When I've completed the routing, you can see things like the embedded net names again. So this next example, what I want to do is I want to come out of, I've got a bus here. I've already routed some items and maybe I've made an ECO or I've just forgotten to route this object. So I need to use standard things like push, shove and hug. So we'll invoke the add connect command again. We'll start to route, and you can see just me pushing this track. It will push the track out of the way to create the space that I need when I'm routing. If I try to push this track, it's not going to allow me. And if we actually look down at the command line, it's going to give me a clue here. I've got a fixed C line, which means that this object has been fixed, so I don't want to be able to use this or push this out the way. So we can use the standard push, shove and hug just to work our way through the bus, get round and finish the routing. So when I come out of this pad here now, I'm going to continue this routing. What I want to do is I want the freedom to be able to do exactly what I want. As a PCB designer, I should know what I'm doing. So I'm literally just going to come out. Maybe I can come out quite an unusual angle. And as I route that, that's giving me the freedom to do that. That's fine. But obviously the disadvantage of that is I've made a manufacturing issue here. I've got effectively potentially a sliver, which probably isn't very good. So I've got a few ways to detect this. Let's just cancel that. If we go to setup and constraint modes and we look at the design, there's actually something called an acute angle detection option, which allows me to effectively set a minimum angle. So you can see I obviously get a minimum angle from pad to line. So it will report a DRC if I actually did something that I shouldn't allow myself to do. But I can also do things when I'm routing. There's something called the enhanced pad entry that stops me from kind of making this type of error in the first place. So you can see the track actually is just snapping back to the legal exit points. Obviously I'm coming out directly, but you can see it just snaps back to where I'm actually allowed to come out from. We'll then continue the routing all the way through using the standard push, shove and hug. And just finish our routing here, and we're done. The track then takes on this assigned colour. It's an overriding colour that you can apply to any net or any object inside PCB Editor, and it allows you to effectively quickly locate your tracks in a design when you're doing a peer review check. We'll go back to the single layer select mode and we'll turn on our ground plane. So we're going to do some routing through a dynamic ground plane. I want to pick this net and start routing, and you can see that the copper shape dynamically updates to make any clearance as I'm routing through the copper. So I haven't got to worry about repouring the copper afterwards or doing it as a post-process. It's all instant. If I've made a mistake, I can literally use a right-click oops or press the F8 key. So we'll just press F8 to undo those objects, and the copper shape repairs itself. And we'll carry on a little bit further. We'll double-click to add a via, go to inner layer 1. So that layer wasn't turned on. But what the tool does automatically is it turned it on for me because that's the layer I want to route on, and it's going to show me what it does. So if I start to affect anything, push, shove and hug will stop me from creating a DRC error. Okay, this next section is going to allow me to do something called, let's just update the shapes, allow me to set up routing specifically for a Flexi-rigid. So the OrCAD PCB Professional allows me to effectively define the cross-section or thickness of the PCB, the stack-up of the PCB by area, allowing me to have kind of a rigid part of the PCB and a flexi part of the PCB. If we go to effectively the cross-section editor, we can get this from the setup menu or from the icon or by typing the command. I get a full breakdown of the actual layers of my PCB. So you can see here I've got 6 electrical layers, I've got some solder masks, some silk screens, some paste masks. I've also got things like some cover layers and adhesives for the flexi section, cover layers and adhesives for the flexi section on the bottom, but also some stiffeners and epoxies. I've got a different type of glue for a stiffener section. I've got different portions or areas of my PCB, and I can add new ones by clicking on the plus to add a new area. And then I enable layers based on what I want. So obviously in my primary section of the PCB, which is the main part, I'm only enabling the inner layers. If we actually go to the tab, you can see that this effectively I just have the 6 electrical layers, the paste, the silks and the solder masks. If I go to Flexi 1, all I get is inner layer 1 and inner layer 2, which are the 2 layers I need for my Flexi, plus the cover layers and adhesives. The stiffener is very similar to the Flexi, except I'm using a different epoxy and stiffener on the bottom versus a cover layer and adhesive. The key part here really to remember when I start to do placement and routing is that this is effectively the top half of the Flexi and the bottom half of the Flexi. This is the top half of the rigid part of the PCB and the bottom half of the PCB. I can add any layers that I like when I need to. It's as simple as a right click, add layers, that allows me to effectively choose whether I want to add things like conductor layers, and you can see all the different layers here, dielectric types or masks. And I can do things like, there's some default design layers that Cadence already defined for you, things like stiffeners and paste masks, solder masks, etc. Or there's something called a site-defined area where I can customize and choose my own type of layers that I want to add. I can edit those site layers, so if I go to edit site file, there's a list of all my custom defined layers, so I can build up the own layers that I need. And I can also do things like I can import an IPC 2581 file. If your fabricators or PCB fabricators are using Polar, this tool many fabricators use to define things like the impedance for a specific cross section of the boards. They can export an IPC 2581 file, which you can then import directly and use that information. So you haven't got to set this up yourself. You can use the information directly from the fabricator. And if we go to the primary section, for example, and look at the signal integrity option, when we're starting to do things like impedance, using this information accurately can give you inaccurate impedance using a BEM2D field solver. So once our cross section is defined, we then define areas for what each section is. So effectively I have a primary section of the PCB, I've got a flexi section here, and then I've got a flexi stiffener section here, and then that then becomes the areas, so they then become intelligent based on what I'm trying to do. So if I was going to do some placement, for example, what we'll do is we'll take this capacitor just as an example. If I place this in the main rigid part of the PCB, I place it on the top of the board, it places it onto the top side, or top of the board, as you would expect. If I mirror that, it would then go to the bottom, which is the bottom side of the main part of the PCB. If I take this across into the flexi section, you can see effectively that then places it onto inner layer 2, which is the bottom side of the flexi, and if I then mirror that, it then goes to the top side of the flexi, which is inner layer 1. If I bring it over here, it goes to the top of the board, top of the flexi, top of the board. So it's what they class as dynamic placement. It's intelligent enough to know which layer is the top of which section of the board. Let's just place this back using the snap pick tool. So we'll then place the capacitor where it's supposed to be. From a routing point of view, obviously if I'm routing on the main part of the PCB and I add a via, I get the availability of all 6 layers because they're part of that main section of the PCB. We'll just cancel that one. If we come over into the flexi section and I do a similar type of thing, this time I double click, all I'm getting is effectively, because it's a 2-layer board, it goes directly to inner layer 1 or inner layer 2, so it's swapping between those 2 layers. You can see obviously the only 2 layers that I have available to me are 1 and 2. I'll just oops that, I'll cancel that. So that's dynamic routing and dynamic placement in flexis. So I now want to effectively route this bus through my flexi section. So what we'll do is we'll literally just window select these connections again. So standard push, shove and hug will hug to the route keeping. The route spacing isn't quite set. I could play about with Constraint Manager for that, but I want to follow this flexi outline. So I can use a really useful feature called right click contour that allows me to use the route keeping with an extra gap. And then you can see I can just guide my mouse all the way around the flexi, get to the end. I'm coming out, so I've got a rules by area, constraint region. I can double click to add my vias again. We'll go to the top layer. We'll then go into single trace mode, and I can then use the right click options. We'll change the bubble here from specific shove to hug, and then I can start to finish my routing as I come into the bus. Once that's complete, we can then move on to the next section. So I've got an RF trace here, and what I want to do is I specifically want to shield this RF trace with some vias. So there's a useful command called place via arrays. I can either do a matrix, which would effectively, if I wanted to stitch all my ground planes together in certain areas of the PCB, I would use the matrix option. In this example, I want to use a boundary. A boundary allows me to effectively choose an object, like a track, a C-line, or I can use the board outline and add lots of EMC vias, for example. In this example, though, we're going to use this track, so we'll enable a DRC check. We'll choose the net we want the vias to be associated to, and then I have to pick a via from that list controlled by that net. I can then choose I want it on both sides of the track, and then I specify a couple of default values. So maybe I want 1 millimeter from the clearance of the vias. When I click the object now, I get a preview of what's going to happen, but because it's a preview, I can actually make adjustments. So let's maybe reduce these values a little bit, put the vias a little bit closer. We'll have increase the number of rings to 2. We'll maybe drop that down to 0.7. So I actually get quite a reasonable placement of vias. When I'm happy with what I want to place, I simply just do a right-click place, and the vias get placed. Because I enabled a DRC check, any that would cause a DRC are automatically removed, which can save you some time. I'm now going to route a track, and we're going to take this into a BGA area. So obviously I've got quite a thick default track thickness. When I go into the BGA area, I'm never going to be able to fan out this BGA correctly or escape this BGA correctly based on this track thickness, so I can use something called a constraint region or rules by area. You can see as soon as I enter the BGA, the track automatically necks down to the thickness and to the spacing between the 2 traces to allow me to meet the constraints that I need to get the routing done. I can also do some useful things like window select groups of tracks already, but I'm getting bored of routing now, so let's just do a right click and finish, and we'll finish the routing. It won't change any layers for you, but it's a quick and easy way to get some routing done. I now want to route a differential pair, so if I individually select a single connection of one of the pins, the pair jumps together based on the rules from Constraint Manager for differential pairs. I'm also getting some heads-up display for phase tolerance, total edge length and relative propagation delay, and these values will update as I start to route. I can also use a command here called right-click scribble, which actually allows me to just guide my mouse where I want it to go. As soon as I make a left click, that routing is then confirmed. So what we'll do is we'll just pan down. If we're not happy with where we're going, we can obviously just go back along the scribble path until we're happy, and we'll guide it all the way down to where the vias are. When I click to confirm, the via is then, or the routing is then completed, and I'm done. We'll just go back into etch edit mode. I've got a couple of DRCs here for the length matching on this differential pair. So we'll hover over the trace and we can do a right click delay tune. Let's set the options to maybe full arcs, and I can get some arcs coming in to try and sort the length out. I'm meeting the phase tolerance but not the other two. I haven't got enough room in here, so what we'll do is we'll move to a different part of the PCB and continue with the delay tune. And you can see the delay tune, or the heads-up displays, going from red to green, red to green. When I get them all green, I know I'm meeting the constraint and I'm good to go. The final part of this webinar, we're just going to talk about some blind and buried vias. So we'll start to route out of this via. Let's turn scribble mode off, and we'll go to inner layer 1. And then we'll just route up to some free space. And we want to change layer now. Let's show some blind and buried vias. This rule has this net has a specific rule that allows me to place some blind and buried vias. So when I double click, I go from effectively inner layer 1, which is the third layer effectively, to the top layer. It's going to add 2 blind and buried vias, one from 3 to 2 and one from 2 to 1. We'll do that again, so we'll go from effectively the top all the way to the bottom, and it's going to add an array of vias automatically. To save me manually having to do that, it's all an automatic process where it adds the vias in an automatic flow. What we'll then do is we'll just select the net, do a right-click 3D view, and we can get a 3D visualization of actually what's going on. So you can see here I've got a row of my 5 vias individually from a blind and buried point of view. There's the 2 vias coming up, and as an example, that's a typical kind of through-hole via. That concludes this webinar.